So in Lewis theory, we're focusing on the valence electrons. Remember, the valence electrons are the outer electrons in an atom. And for main group elements, we can predict how many valence electrons there are by looking at the group number for that element. So we represent those as dots surrounding the chemical symbol for the element. And that's called a Lewis structure or a dot structure. So let's look at oxygen. So first let's write the electron configuration for oxygen. So if you find oxygen on the periodic table, what block of the periodic table, S, P, D, or F, does oxygen sit in? It sits in the P, and it is in row 2, so that tells me that its electron configuration ends with 2p something. So if I look at the first row, I see hydrogen and helium. That's the first row, the S block, and so that's 1s2. And then I go to the second row of the periodic table, and I see lithium and beryllium in the S block. The second row, 2, the S block, S, and there's 2 squares there that I have to pass through on my way to oxygen. You can think of this as like following a trail in numerical order through the periodic table until you get to the element that you're looking at. So after the 2s block, still on that second row, I get to the p block. So this is 2p, and to find the superscript, I count over until I get to oxygen, and it's 1, 2, 3, 4, or 2p4. Any questions about how I did that? We can double check this by adding up the superscripts. 2 plus 2 plus 4 equals 8, and oxygen has 8 electrons, so this is good. So when we look at this electron configuration, we should be able to recognize how many valence electrons there are. The valence electrons are the ones in the highest occupied energy level. In terms of the quantum hotel model, it's the highest floor that has people staying in it. So this is the first floor, the second floor. This is a different room, still on the second floor. There's nobody staying on the third floor. So we just count up the people or the electrons on that floor. So it's these guys right here. Those are the valence electrons. And there's 6 of them. And if we look for oxygen in the periodic table, we see that oxygen is in group 6A. It's in group 6A. It has 6 valence electrons. Everybody cool with that? So when we represent oxygen as a Lewis structure, what we're going to do is we're going to write its element symbol. Oops, wrong pen. Oxygen. And then we're going to take those 6 electrons and make 6 dots around the element symbol. So we tend to go, we use the top, the bottom, the right, and the left, and we'll understand why later. So 1, that's not quite big enough. Try again. Making those dots can be a little bit of a pain. 1, 2, 3, 4. So that's top and bottom, right and left, and then there's some that are going to have to be paired up. So there I have 6 dots. So that's the Lewis structure for oxygen. You can put the electrons anywhere around in the top, bottom, right, and left positions, but you should put them around one at a time first and then pair them up. Any questions? Mm-hmm.
Does that like represent anything as far as like whether it's placed or it's just this matter? This is only illustrating the amount of electrons.
Well, it illustrates the amount of electrons. It also ends up illustrating the number of paired and unpaired electrons. Let's look real quick at the orbital diagram. So if we look at an orbital diagram just for the valence electrons of oxygen, oops, that's not an S, that's a P. valence electrons, there are 6 of them. 1, 2, 3, 4, 5, 6. Right? So when we look at the valence electrons, we see that these electrons are paired, those electrons are paired, and then these 2 electrons are not paired up. And when we follow this pattern of going one on the top, one on the right, one on the bottom, one on the left, and then doubling up as needed, we end up coincidentally doing the same thing. So here we have a pair of electrons, a pair of electrons, a single electron, and a single electron. And it ends up mirroring what's going on in the orbital diagram. So it just kind of happens for you without thinking about it. And what we're going to see is that from this Lewis structure for oxygen, we see these 2 unpaired electrons. That's going to tell us that oxygen is usually going to form 2 bonds. Those unpaired electrons are the ones that are actually going to form the bonds. So it helps us in drawing Lewis structures later. Any other questions? So each dot in the structure represents a valence electron. So you put the dots around a maximum of 2 per side. Exact location isn't critical. If you put the unpaired one on the top instead of the bottom, that's fine. But put the dots in singly first and then pair them up. And it's really important to follow this convention when you're doing mastering chemistry homework, because mastering chemistry cares about this. So an atom with 8 valence electrons is particularly stable. How many valence electrons do the noble gases have? 8. And the noble gases are very unreactive. They are considered inert. They don't react. And so that's a very stable configuration. And we call 8 dots an octet. It's like, 8 people singing together is an octet, right? So we're going to find out that 8 is kind of a special number for electrons.
I think that's not critical, but you said it should be top, bottom, left, right.
Yeah, so let's just go back to this guy and see some other ways that would be entirely acceptable. So you could end up with the unpaired ones like this. You could draw it like that. That's fine. I tend to, foresee how many there are going to be. It's a little bit like playing dice, with dice, right? You know what 6 looks like because of the arrangement. You don't actually have to count them anymore. So when I know 6, I know that there's going to be 2 paired and 2 that are unpaired. But when you're making this, start wherever you want, but put them by themselves first, and then pair them up however you want to. Oh, I drew the same one. Let's just make it different. No, that's the same one too. Gosh, I'm not very creative today. So exactly where around the oxygen you place these in terms of, are they opposite of each other? Is there a pattern or anything? That doesn't matter. Does that answer your question? But if you just go top, right, bottom, left, and then keep going, you'll end up with it correct. So we're going to write Lewis structures for the first 10 elements. Thankfully, this goes a lot faster than writing electron configurations. So how many valence electrons does hydrogen have? Just 1. So then the Lewis structure for hydrogen is just, we got 1 dot. How many does helium have? 2 dots. How about lithium? 3. How about beryllium? Wait a minute. Valence electrons.
Lithium has 1.
Yeah. That's number of electrons. So lithium has 1 valence electron. Beryllium has 2 valence electrons. Boron has 3. How many does carbon have? Valence electrons. 4. It's the group number. So 1, 2, 3, 4. Nitrogen has 5. 1, 2, 3, 4, 5. We've seen that oxygen has 6. It's got a little off center. How many does fluorine have? 7. So after you do this a couple of times, you recognize, well, 7, that's going to be one that's not paired up and the others are paired up. So then you can stick them in a little more symmetrically, and those are probably a little too big for the letters. We want to avoid like making circles of electrons because it's hard to see how many. We don't want to have to count them. We want to just be able to look at it. How about neon? 8. So yeah, I'm going to make this a little smaller. So it's going to have pairs on all 4 sides. And that's where the 4 sides come in nicely, because then you get pairs on all sides. That's your octet. Neon has an octet of valence electrons. It is particularly stable. I think of it as being happy. So neon is a noble gas. Neon is happy with 8 electrons. Fluorine has 7 electrons, not as happy. Fluorine would like to get 1 more so that she can be like neon. Helium is very stable with an octet, not an octet, a duet of electrons, because helium's very small. And so there's only 2 electrons, but that is a full valence shell. The highest occupied level is the first level, and it's full. Okay, any questions? So in Lewis theory, we represent chemical bonds as sharing or transferring electrons to obtain a stable configuration, which is usually 8 valence electrons. So in an ionic bond, we have transfer of electrons. So one atom loses 1 or more electrons to become an ion. The other atom gains 1 or more electrons to become an oppositely charged ion. And then we have opposite charges that are attracted, much like magnets are. That's an ionic bond. Covalent bonds. Co is a prefix that means sharing, and valent refers to valence electrons. So a covalent bond involves sharing of valence electrons. So this is an important distinction. There might be a test question involving that. So the octet rule says that in chemical bonding, atoms will transfer or share electrons in order to obtain outer shells with 8 electrons. As with other things, the smaller elements sometimes violate this rule. So hydrogen, lithium, and beryllium follow what we call the duet rule. It's like the junior octet rule. So hydrogen is just trying to be like helium with 2 valence electrons. Helium is cool all by herself, and then lithium would like to lose an electron and become like helium. So they're trying to become like the nearest noble gas. So let's look at the Lewis structures for magnesium and for sulfur. So what group is magnesium in? 2. So how many valence electrons does it have? 2. So let's give it 2 valence electrons. Yes?
I thought hydrogen was the one that had 2 and helium had 8.
No, helium only has 2 electrons. Okay. It's in group 8. And so that makes us think that maybe it has 8. But if you look at the atomic number, it's got 2 protons and only 2 electrons. Okay. So there's magnesium. What group is sulfur in? 6. So in group 6A, it's got 6 valence electrons. 1, 2, 3, 4, 5, 6. I'm kind of random sometimes in how I put those around. As long as you place the dots top and bottom, right and left, You should have 2 that are pairs and 2 that are singles, a total of 6 dots, and that's good. Any questions?